Good morning, everyone. We are going to be resuming reading about the internet domain sockets in the Linux programming interface. We left off on chapter 59, section 5. We still got quite a bit in this chapter. A lot of it is review for me. Like, they have a whole section on DNS, which, you know, I've spent a lot of time with DNS in my career here, so I'm not going to probably get much from that. The getAddr info, I've ran into that several times. Go used to have a dependency on that, the libc getAddr info, I think, at one point. Let's see. Then they have some like client server programs to show how to set up basic TCP server probably. And then I guess they go in and they set up a bunch of library code, go over some obsolete APIs, and then have a discussion about the difference between internet domain sockets and Unix domain sockets. So yeah, still got quite a bit of material to cover here. And then we still have server design and advanced topics. So today I want to get through certainly the internet domains chapter. and potentially the rest of the sockets if we have sufficient time. Let's see, that would take us, that'd be an 89 page day, which is certainly doable, but in the past I've only been able to do that by skipping doing exercises and also kind of reading really fast. So I think today I'm going to take it slower, do more exercises to kind of like solidify things that I'm learning. So I think getting 2 advanced topics would be the goal for today. And then Wednesday will be advanced topics and terminals. And then Thursday will be alternative IO models and pseudo terminals and the rest of the stuff in the book here. So yeah, we're nearly complete with this book. It's been quite the project. I'm glad I did it. I'm not done with it yet, but given that we're a good chunk away through the book, I've been reflecting on the progress I've made, and I'm glad I did it. It's given me a lot of exposure to the Linux syscall interface that I wouldn't otherwise have encountered myself. It's got me doing more C programming, very comfortable with writing some of those basic C programs. And I think this is a good exercise, but looking back on it, I don't regret doing it, but I wouldn't advise other people to do what I did, which is to read through like cover to cover. Unless you have, I wouldn't advise it because the book is very dated. Like I wouldn't say like it's obsolete by any stretch. Like it's still in print, and he's kept it up to date here and there in different areas. But you could tell it is a book of its time, which is the late 2010s, or I guess 20 aughts, the late aughts. I think it was published in 2009 or 2010. I think. Let me go back here. Its original publication date was 2010. So it's definitely like a book of its time. And it doesn't cover a lot of the really incredible advancements in Linux in the past 16 years since it was originally published. I'm thinking about things like BPF, containers, what else? I guess, let's ask AI. Let's see. What are the major advancements in Linux in the past 16 years since 2010? Let it bake on that for a little while. Yeah, the container native stuff. It doesn't really go into a lot of the security hardening things like AppArmor or SE Linux. I think it's called SE Linux. So like those topics are kind of like not even covered in this book. I think they kind of allude to them and reference them here and there, but security hasn't been a huge focus of the book, which I don't blame them. But I feel like containers, like namespaces and C groups, are like major areas of the Linux kernel that need to be covered in a book like this. And he does have material on his website, and he does do training on those topics, but it's missing from the book itself. So that's the one thing that I would say like is major thing that's missing. Let's see. Yeah, containers and names, C groups, namespaces, seccomp, Um, all the stuff that's like what you consider container technology wasn't covered. And we're already on C groups V2, and he doesn't cover C groups V1 in the book. Yeah, it invented them, but there was a lot of prior art with BSD jails and Solaris zones, like, and even Cheroot. Like, there's a lot of prior art that I wouldn't say this is it. Yes, they invented containers, but only many, many years after the prior art had already established it was a good idea. Yeah, the eBPF stuff, exactly. I feel like these are the two things that were like major to the kernel. BTFRS maturity for sure. The networking stuff I'm not really familiar with. Those advancements. I would have liked to have heard him talk about some of the things like SE Linux, AppArmor, LaneLink I'm not even familiar with. SecComp, but also things like kernel address space layout randomization, or just ASLR in general. I feel like that would have been helpful because he does present several like diagrams in the book that show how memory is laid out, which I found very helpful for my understanding of how memory is laid out, like where stack is, where the data sections are, where the heap is, where mmap areas are. Things like that, where thread stacks are located. But like this abstract address space layout randomization. I don't know why I say abstract. Address space layout randomization, I don't really know the details of that. All I know is it makes it to where like it's harder for programs to get exploited. So it would have been nice to have like a section on that, kind of just explaining ASLR in general. Systemd is such a massive topic. I don't even know if he would be able to cover it in a book like this. And Systemd is not Linux per se. It just happens to be the init process that everyone uses now. I think rewriting the book with a focus on Systemd, because he did have sections on like logging and stuff using syslog, which I'm sure those things are still valid with journald, but it's just like there is no longer a syslog. There's like a journald thing. So having an update on logging and maybe some of the Systemd stuff would be nice. Yeah. Again, containers and eBPF, I think, were the two main things that I would have liked to see him cover. And like I said, he does have content on his website. So I'm not actually reading here. But I kind of wanted, these are things that have been bouncing around in my head. He does have Sorry, this one here. I don't know why I just think go to man7.org. That's his website. Yeah, between 2004 and 2021, the author was the maintainer. Okay, so that's just saying that he moved on from the man page project. Bit of a distraction here, but I think I can. I'm gonna close out his blog. This seems like just a bunch of API changes I'm not going to look at. How long did it take you to write the Linux programming interface, and why did you write it? Several years, although the project was somewhat interrupted by various life events. The book was largely complete by 2006. So again, like, I mean, he updated it for the release probably, but his mind was in the 2006 time frame when he wrote the book, and it was largely complete by 2006. So it's even more dated. It's probably like 20 years old now. Can you please help me review debug my code? Yeah, I mean, yeah. I think he does do virtual courses now. If you go here, let's go back. Training courses. I think he has virtual courses available. Yeah, online here. I guess what he means is like go at your own pace type thing, versus what he does is more of like a webinar type thing, I think. e.g. more socket options, tracing, and debugging techniques. Okay. And POSIX asynchronous I/O. Oh, there. Two volumes. $13.27. Oh, we're not even there yet. That would probably be the evented I/O stuff. Okay, let's do. I'm gonna delete this because I haven't even started reading. Man, AIO. Let's ask AI. High level, what is POSIX asynchronous I/O, and how does it differ from select epoll in Linux? IOU ring. Okay, that's cool. Linux largely skipped POSIX AIO evolution and built IOU ring. Real kernel level asynchronous IO supports file sockets, timeouts, polling, send, receive, splice, except connect. Conceptually, IOU ring is what POSIX AIO wanted to be. I haven't really heard about this IOU ring stuff. I'm gonna open another AI here. We'll do or maybe just man it. Man IO U-ring. Okay, so oh, that's where man 7 comes from. It's the 7. It's more the prose, like conceptual stuff. 7 here comes from the 7 up here. Rust. Why is that Rust? Okay, so maybe we do man W7 LS, or sorry, IOU ring. Okay, so now we got that. There's man 7 right there. Z-less, I like that, Z-less. Or Z-cat. So cool. I like Z-cat. Because cat will just give you back the binary, right? Should, yeah. Z-cat into less. Written? Okay. This dude wrote it. But if we go under, let's say, CD under user share man 7. So there's like a bunch. Oh, ZMQ. Oh, interesting. I guess that came with the ZMQ package I installed. But if I just go through each one of these gzip files, so I'll just say ls grep or ls star.gz, and we'll pipe that into while read align do zcat $line, and we'll do a head n2 done. We'll do echo $line, and then we'll zcat as well. So why is it freaking out? Oh, because we gotta do that. Okay. And we'll do here instead of head, we're gonna do grep -I for author. And we'll grab the, I think C10. Grep for Karisk. He's got to be at least one. How about instead of doing this grep here, I just zcat it and then grep for Karisk. He's only in one man page in man 7? That seems unrealistic. Okay, well in here we can do, instead of doing that, we'll do a find iname. It's going to be star.gz. I would think he would have like a huge volume of man pages that he's attributed, but there's just a handful here. Not what I expected, but maybe I'm grepping the man pages in a way that's weird. Alright, clear that. I did want to read about IO Uring. To IO Uring. Sorry, IO. Sorry, man 7. Yeah. And then let's continue reading here. Select poll epoll, tell me when I won't block, and I'll do the work. POSIX IOs do the work IO for me. I'll check back later or get notified. IO Uring is queue work to the kernel and get completions at scale. So IO Uring is the way to go. When to use what? Network servers, epoll, or IO Uring if you're modern. Portable POSIX code is select and poll. And then async file IO using POSIX AIO with caveats. So basically IO Uring is the thing that's, you know, I'm not writing portable code, so I don't have to worry about that. And IO Uring seems to be the best way of doing asynchronous IO. If you want, I can sketch how POSIX AIO is implemented under the hood on Linux. No. Compare POSIX AIO versus Go's runtime netpoller. Show what async disk IO is fundamentally different from async sockets. Do that. basically abandoned in practice. Yeah. Send file splice workflows. Yeah, I was gonna say, like, on Linux, I know it uses epoll. I've seen that in the strace output, and it uses splicing as well. I think that's a big difference in my mind between Go's model for asynchronous I/O is that it presents this very simple blocking, and it is blocking. I know they say here that it's like blocking looking, but it is blocking code. Your reads block that specific Go routine, but it doesn't block the system from making progress in totality. I guess that's the difference. And even in like normal I/O, like blocking I/O, when you block a process on a read call, for, say, the kernel like doesn't run you like you're blocked on reading. You're not running on the CPU, but the entire system makes progress. And so I actually prefer the blocking model, as long as the system in total makes progress. That's the key. Like, does the system in total make progress? And that's the model that was established with regular blocking I/O. I feel like is the model that Go presents to the programmer, but the implementation of those blocking I/O reads and writes is such that it's very performant. Like, you can spin up like tens to hundreds of thousands of Go routines and have them block on I/O or whatever, and it's not like a huge performance penalty. Whereas if you did that with processes or even threads that you manage yourself, like, it's gonna have a lot of overhead. And to contrast that with other models, like JavaScript originally had like a callback model where you perform some I/O operation and you'd pass it the callback that would then get invoked when the IO operation is completed. Like you have that model, and then you have this kind of like async await model, syntax and model for like for code that wants to kind of look like it's blocking somewhat, but also allow for like non-blocking cooperative scheduling of the code. I mean, to be honest, like I've only really done a lot of async await in Python and JavaScript, and both of those are very heavily reliant on event loops. And so in that concept, you have a loop, the language runtime provide, or in Python you can provide your own event loop, but an event loop exists that's going through running code, and when you call async and await, like await will yield to the event loop so that it can continue running. So your process is never getting, your thread of execution is never getting put off CPU because of the IO. Whereas with Go's runtime, when you do an IO, that thread is then basically put off CPU by the operating system, and Go spins up a new thread and then starts scheduling Go routines onto it. And so you could have like, dozen or more n number of threads that are operating system threads that are just waiting for IO operations to complete. So, I mean, to be honest, I don't know the details of how Go's runtime does all that work. I think that would be like several months probably of research that I could do, just learning about Go's runtime and scheduling and how it performs IO. But just as a user of Go and a user of JavaScript and Python async capabilities, I much prefer Go's model, like programming model. I guess the problem is that there's this huge amount of complexity between the programming model that Go presents you, which is very simple and somewhat easy to reason about, and then all the implementation details that are in the runtime that allow that to actually function. Yeah, I guess. Yeah, I prefer Go's model, but I'm curious what the Zig community is gonna end up with for an asynchronous model. It's not even IO; it's also asynchronous computation. Like sometimes you just want to spin up a lightweight thread or Go routine or whatever, and have it just do computation independent of your current thread of execution. So, like, I like the threading model. I feel like Go routines map onto the threading model very well. I don't think there's anything broken with that. I think what happened is like the threads weren't able to perform, so these other languages came up with like event loops that allowed for all these concurrent IO tasks that need to be completed to be managed by that event loop. But now you have to write your code in such a way that it is cooperative with that event loop. Because if you indeed block, like a hard block, then you seize up the event loop. Or if you I guess the other downside is that you now have like colored functions where you have functions that are async aware, and then you have functions that are not async aware. And calling in between those two, like obviously async code can call into synchronous code with no problem, but synchronous code calling into async code now presents like difficulty because you have to have that event loop going. Hey Sushi, what's up? Yeah, I was just kind of going through learning more about the different asynchronous IO models in Linux. And I was just chatting with ChatGPT here about the differences between IOU ring, POSIX AIO, which I hadn't heard of before, and the Go's Go runtime, and like how they're different, basically. Yeah, this netpolar part of the runtime. And I got on this tangent because I was reading over some of the FAQ in Michael Karisk's website, and he was talking about POSIX asynchronous IO and why it's not covered. And so I was like, oh, I've never actually heard of POSIX asynchronous IO. I guess it was intended to be a standard that all the different Unixes could adopt. So on Mac OS or on BSD or on Linux, you could have the same API portable across those different operating systems. But what ended up happening is it basically just failed. And like everyone went their own ways. So Linux went the way of IOU ring and EPOL. Mac OS and BSD, they went the way of KQ. And then like Windows, I guess, has its own version as well. I forget what it's called. But basically, POSIX asynchronous IO is like a failed thing. And a lot of it was implemented in user space, and like it was not performant at all. But IOU ring seems to be like the new hotness when it comes to asynchronous IO inside the Linux kernel. It's Linux specific. And just from like my really like cursory review of it, it seems to be some type of like ring buffer that you put like IO operations into, and then the kernel does those IO operations asynchronously and then like writes to that buffer, I think. But yeah, I'm not exactly sure. I'm gonna read the man page here in a minute. There's a mention by the AI, by ChatGPT down here, that Go is actually switching over to it. I was actually S-tracing a Go program the other day, and I saw that the I/O that it was performing was using EPOL on Linux and something called splice, which is kind of like send file, but it's more of a generic form of send file. I can maybe pull that up here. Let's see, my name, I forget where it was at, but I think it was this Echo server in chapter 56. So if I go run, actually I'm going to S-trace this. I'm going to build it, make, and then I'm going to S-trace -f build, and where is it? Echo here. So these are all the syscalls that the Go runtime is making on behalf of me, my program. And you can see it's doing all this EPOL CTL stuff here. There must be like an EPOL P wait. Here we go. So it's doing a lot of EPOL stuff. And then when you actually look at, let me pull up another terminal here. What chapter is this again? I forget what chapter it was. 56. If we go under chapter 56 and we just run the build hello here. Wait a minute, is that the wrong one? No, I was using netcat. Netcat. What port is this thing on? Netcat to localhost 12345, and I just say oops. So as soon as I connect, it comes out of that EPOL wait and then does a bunch of stuff here. And then if I actually send it a line here, say like hello world, it echoes it back to me, and it uses this syscall called splice. You find Go a little bit overrated. Yeah, I mean, I find like all technology, it's like use the right tool for the right job. Why do you say it's a little bit overrated? Kind of curious what your thoughts are. A little bit of background on me. So I started using Go back in 2015, around that time. And I used it to implement a bunch of power management software for a data center I worked at the time. And then I joined this cloud computing company in 2016, and I basically did nothing but Go when I joined that company for a solid 4 years until 2019. And then I joined this other company. It was like a crypto company in 2019. And then I did probably like 90% Go until about 2024. And so I have a lot of experience with Go. But obviously, I'm not like a zealot. I don't really, just because I'm familiar with a tool doesn't mean it's like the best thing in the world. I am curious though, like how they implemented a lot of this stuff in the Go runtime, because Go's concurrency model and its asynchronous IO is atypical, I found, in many programming languages. Like it seems like most programming languages have gone down the path of using like async await syntax, and then the implementation of that is either like an event loop in the case of JavaScript and Python, or in the case of Rust, it's like compiled into this like state machine that's like ran by the Rust what do they call it? Asynchronous. I forget what they call it. But like basically like their asynchronous runtime that they have. And that thing is like pluggable. But yeah, it does seem like Go's approach is a little bit different. So going back to the ChatGPT thing here. So it says why Go hasn't fully switched to IO Uring. So it says because Go already has scalable networking, cheap concurrency, and good latency. And IOU complicates portability because it's Linux only. Complicates runtime invariance. Helps more with file IO than sockets. So basically, like they're adopting it for file IO stuff, asynchronous file IO. It's interesting. The real deal, but sharp knives. Sometimes ChatGPT is a little bit too flowery in its language. Okay. Okay. Well, I'm going to kill that. Oops. I hit the wrong thing. I always do this. And then I can't figure out how to get out of this. Maybe if I do Command Shift 2. Oh God. This is one thing. This is Hyperland. It happens occasionally that it'll do this, where it like fogs the screen on me, and I've been able to figure out how to escape it before, but it took me like a hot minute to figure out. I don't want to restart Hyperland because I guess I could do like an update and restart it. I really wish it wouldn't do this though. I think I did it last time. I did it like, well, maybe if I just do this, does that help? No. Oh, this isn't okay. Let's trash that. There we go. I don't know why it does that. Okay, let's go back over to here. Okay, I'm gonna kill this. Kill this. Kill that client. Go back here. clear. And we were going to read the man page for IOU ring. This seems like 1, 2, 3, 4. Oh, there's a big example at the bottom. I'm just going to read the initial description. So IOU ring is a Linux-specific API for asynchronous I/O. It allows the user to submit one or more I/O requests, which are processed asynchronously without blocking the calling process. IOU ring. See, this is the thing that I don't quite understand. Is like, you can do asynchronous I/O with regular file descriptors, regular syscalls like read and write, as long as you like have like the non-blocking flag set. Like, those operations will not block. So I'm kind of curious, like, if you use the non-blocking syscalls, like read and write syscalls, and then you also use like epoll to get notified when those file descriptors are available to read and write, like, why is that not just good enough? Like, why do you need this IOU ring thing? Let's see. IOU ring gets its name from the ring buffers, which are shared between user space and kernel space. This arrangement allows for efficient I/O while avoiding the overhead of copying buffers. Okay, so that is one advantage, is that with traditional read and write operations, you're making a lot of copies between user space and kernel space memory. Even if you have the non-blocking flag set, like, you're still copying all that data in and out of the kernel. Whereas IOU ring apparently shares the memory between the kernel and the user space, so you don't have to pay like the cost of copying all that data, which is nice. And I guess, the ChatGPT mentioned that the IOU ring obviated the need for stuff like send file and splice. And I was thinking when it said that, I'm like, okay, why is that? Well, if you think about it, send file and splice are both syscalls where you hand the file descriptor to the kernel and tell the kernel, you do the IO in the background, like inside the kernel. Don't like read from like user space memory for doing the IO. So that's another way of like getting the amount of copying in and out of the user space, like eliminating that. But if you have like shared memory with the kernel, then the performance overhead of using something like splice or send file, like that whole family of syscalls, might be like, the benefit might not be worth it at that point if you have shared memory with the kernel. All right, let's continue reading here. So we avoid the overhead of copying buffers between them where possible. This interface makes IOU ring different from other Unix I/O APIs, wherein rather than just communicating between the kernel and user space with system calls, ring buffers are used as the main mode of communication. This arrangement has various performance benefits, which are discussed in separate sections below. In a separate section below, this man page uses the term shared ring buffers, and queues interchangeably. So the program model you need to follow for IOU ring is outlined below. Set up shared buffers with IOU ring. I'm not going to read all of this, but I think just reading that initial description paragraph is sufficient for me to understand, at least in the taxonomy of like asynchronous I/O capability on Linux, where IOU ring stands. Basically, it's non-portable, Linux specific, high performance because it's sharing memory with the kernel. It's asynchronous in nature, and it basically obviates the need for doing things like epoll, read and write type non-blocking calls. And it also basically, like, POSIX asynchronous I/O is just like completely obviated because it's like garbage. So I think I have a better picture of what's going on there now. So I'm not going to read about IOU ring anymore, and let's continue on here. reading this FAQ. I don't care about that. Why are there so many errata? Don't care about that. Why do you use the domain man 7? Oh, cool. I took over maintenance of the Linux man pages project in 2004. Since that time, I've expanded the remit of section 7 to include many more pages that give ownership big pictures of how APIs are related. I've written many of these pages myself. I did a scan of that, and only one of the 7 section or section 7 man pages has him listed as an author, which is weird. So man 7 for me is about giving a big picture about Linux APIs, and was the inspiration for the domain name. Yeah. Okay. I wanted to read through his training courses page because I think he had some let's see, he had some like documents. I think it's maybe here. So say we want to learn about containers. Say like C groups. I want to learn about C groups v2. Oh, I got someone coming up to my house here. I'm going to take a quick break to see what this guy wants. I'll be right back. All right, sorry about that. I have people doing some work on my house here, so I just need to let them in. You might actually hear the construction going on, but it shouldn't be too noisy. All right, so we were looking through the training material. So let's see, does he have a containers container? Yeah, system program for Linux containers. Description. I've taken this course before. Oh, this is just part of the module. Okay, I was gonna say, like, he gave us a bunch of stuff in binders. And I was like hoping, because I saved the book, obviously. I was hoping I still had those binders somewhere, but I haven't found them. So I might have like misplaced them somewhere. But I think one of my friends who also took the course might have it. But it's basically like a bunch of slides like this. And he goes through and like he does his own kind of like presentation and treatment of the material. And yeah, he'll give like a lecture about the material, and then we'll go into like exercises and stuff. I think that's the format that we followed. This is back in 2019, so it's been 7 years since I did that, but pretty sure that's how it worked. I think I'll actually reach out to my friend to see if he has the binders if I can't find them. But I would like to come back to that material at some point and like revisit it. But given that I just finished reading 1,200 pages, soon to be 1,500 pages of Michael Karisk stuff, I think I might be done with that for a little while. I mean, he's a great author, but I just want to kind of like get some other writing styles. Get some exposure to some other writing styles than his. This is all like a lot of reading. All right, so let's resume reading. So I'm gonna open up my progress here, go down the bottom. We're 1204 at 10:52. Overview of host and service conversion functions. So I think I remember reading a little bit of this, but maybe not. Computer represent IP addresses and port numbers in binary. However, humans find names easier to remember than numbers. Employing symbolic names also provides a useful level of indirection. Users and programs can continue to use the service name even if the underlying numeric values change. A host name is a symbolic identifier for a system that is connected to the network, possibly with multiple IP addresses. A service name is a symbolic representation of a port number. The following methods are available for representing host address and ports. Host address can be represented in binary value as a symbolic host name, or in presentation format dotted decimal for IPv4 or hex string for IPv6. A port can be represented as a binary value or as a symbolic service name. Various library functions are provided for converting between these formats. This section briefly summarizes these functions. The following section describes the modern APIs, INET, and TOP, which is network to platform? maybe. INET Piton, get attr info, and get name info, and so on in detail. In section 59.13, we briefly discussed the obsolete APIs, INET Aton, INET N2A, get host by name, and get service by name, and so on. Converting IPv4 addresses between binary and human readable forms. The INET A to N and INET N to A functions convert the IPv4 address to dotted decimal notation to binary and vice versa. We describe these functions primarily because they appear in historical code. Nowadays, they're obsolete. Modern programs that need to do such conversions should use the functions that we describe next. Converting IPv4 and IPv6 addresses between binary and human readable forms. The INET Piton and INET NTOP functions are like the Aton and N2A, but differ in that they also handle IPv6 addresses. They convert binary IPv4 and IPv6 addresses to and from presentation format that is either dotted decimals or hex string notation. Since humans deal better with names than with numbers, we normally use these functions we normally use these functions only occasionally in programs. One use of INET N2P is to produce a printable representation of IP address for logging purposes. Sometimes it's preferable to use this function instead of resolving an IP address to a host name. For the following reasons, resolving an IP address to a host name involves a possibly time-consuming request to DNS servers. In some circumstances, there may not be a DNS PTR record that maps the IP address to the corresponding host name. Yeah, Sushi's in the house. So basically, like, this is like reverse DNS, RDNS, and there could be 0, 1, or many reverse resolutions potentially, and a lot of people don't do reverse DNS, so I can see why he's saying that. Might not map to a corresponding host name. We describe these functions in section 59.6 before get attr info and get name info, which performs conversions between binary representations and the corresponding symbolic names, principally because they present a much simpler API. This allows us to quickly show some working examples of the use of internet domain sockets, converting host and service names to and from binary form. Obsolete. I'm going to skip by that because I don't really want to even read stuff that's obsolete. Converting host and service names to and from, okay, this is the modern format. So the get attr info function is the modern successor to both get host by name and get service by name. Given a host name and a service name, get attr info returns a set of structures containing the corresponding binary IP addresses and port numbers, unlike get host by name and get attr info transparently handles both IPv4 and IPv6 addresses. Thus, we can use it to write programs that don't contain dependencies on the IP version being employed. All new code should use the get attr info for converting host names and service names to binary representation. Okay. So there's one function that handles both service and host name resolution. Reverse DNS is so cool when you get to analyze the email servers. If you don't get the reverse DNS, then it will get impossible for mail servers to resolve the domain name for communicating to SMTP servers. Yeah. I've never really used reverse DNS for much, but I did have to set it up. I worked at this data center, and they had a bunch of IPv4 address space allocation. And one of the things that IANA, or it's the North American subsidiary of IANA. I forget the name of it, but they were like saying like we needed for our IP address allocations, we needed to have reverse DNS records set up for every IP, and so I configured, I think it was bind DNS server to respond for all the different CIDRs that we had allocations for. It would respond with a DNS name. So you give it the IP address for the reverse resolution. It would give back the host name, and the host name would just be a part of our DNS for our data center that would then just would then just forward map back to the IP address that it reverse mapped from. So Amazon does something similar as well, from what I understand. But this is back in like 2013, I think. And that's like the only really time that I've encountered reverse DNS. I've never had to actually use it for SMTP. I haven't done much SMTP stuff though. Yeah, it's kind of like a weird thing because like a host name can resolve to multiple IP addresses, either v4 or v6, because you just have multiple A and quad A records. So it's like a one-to-many between host name to IPs. It's a one-to-many relationship. And then reverse is obviously like you give the IP you want the host name. That's a one-to-one. So it's like two different spaces that like they don't like evenly map to each other. All right, let's continue. Did I get on the wrong page here? Okay, yeah, so it's just talking about get adder info. Let's pull up the man page for get adder info. Man get adder info. So the prototype for this is a char star node, a char star service. So that'd be the host name, the service name, and then this thing called hints, which is an adder info pointer, and then res, which is part of the result. I'm trying to get a hold to a VPS provider which can't restrict the SMTP port and open port 25 by default. Because for cold email, and you can easily sell a single mail account for 3 USD. And with US IP, it's better after warm up. Yeah, I have no idea what you're getting up to there. All right, so we got our hints, our result. I think this is it. And these are the same struct. So because this is a const, that means that the hints are read-only for the implementation, whereas this is and it's also a pointer to a pointer. So result itself will be where it writes the result. Let's read the description here. Give a node in service which identify the internet host in service. Get adder info returns one or more of the adder info structures. Oh, it could be more than one. Okay. One or more adder. I guess if you have multiple A records, it might be more than one. Each of which contains a internet address that can be specified in a call to bind or connect. The get adder info function combines the functionality provided by the get host by name and get service by name functions into a single interface. But unlike the latter functions, get adder info is reentrant. That's nice. It allows programs to eliminate IPv4 versus IPv6 dependencies. The adder info structure used by get adder info contains the following fields. So adder length, the adder itself, canonical name, and next. I guess that's if there's multiple. If this is not null, then there would be multiple structures. Where does the service name come in? Because you pass in the service here. Where would that be written to? Huh. And with us, IP is better after warm-up. Yeah, do check these platforms later on. Yeah. Okay. Yeah, I don't fully understand how the service. Maybe I should just search for service. Service. Okay, so the AI family. Okay. That's errors. Oh, okay. So either node or service may be null, but not both. Can you do both at the same time, though? Cool. Okay, here it is. The getAtterInfo function allocates and initializes a linked list of adder info structures, one for each network address that matches node and service, subject to any restrictions imposed by hints, and returns a pointer to the start of the list in result. So that means it probably does heap allocation to do that. Okay. That's enough reading there. Okay, let's continue reading on here. The existence of systems such as DNS is essential to the operation of the internet, since centralized management of the enormous set of internet host names would be impossible. The Etsy services file maps port numbers to symbolic service names. The inet piton and inet ntop functions. The inet piton and ntop functions allow conversion between both IPv4 and IPv6 addresses between binary form and dotted decimal or hex string notation. Pretty straightforward. The P in the names of these functions stands for presentation. Okay, so we go from network to presentation or presentation to network. The presentation form is a human readable string such as the following. The inet piton function converts the presentation string contained in source string into a binary IP address in network byte order. The domain argument should be specified as either AF inet or inet6. The converted address is placed in a structure pointed to by the adder pointer, which should point to either an inadder or in6 adder structure according to the value specified in domain. The inet n to p function performs the reverse conversion. Again, domain should be specified as either inet or inet6, and adder pointers should point to an inadder or in6 adder structure that we wish to convert. The resulting null terminated string is placed in the buffer pointed to by destination string. The length argument must specify the size of this buffer. On success, inet ntop returns dst stir. If length is too small, then inet ntop returns null with error node set to no space. To correctly size the buffer pointed to by destination stir, we can employ two constants defined in net inet in.h. These constants indicate the maximum lengths, including the terminating null byte, of the presentation string for IPv4 and IPv6 addresses. So it's basically 16 for v4 and 46 bytes for v6. We provide examples of the use of these functions in the next section. Client server example, datagram sockets. In this section, we take a case conversion server and client programs shown in section 57.3 and modify them to use datagram sockets in the inet6 domain. So datagram would mean that this is unreliable. Datagram on the inet domain, internet domain, means that it's unreliable. We present these programs with a minimum of commentary since their structure is similar to the earlier programs. The main difference in the new programs lie in the declaration and initialization of the IPv6 socket address structure, which we described in section 59.4. The client and server both employ a header file shown in listing 59.2. This header file defines the server port number and maximum size of messages that the client and server can exchange. So it's got this buffer and port number here. Looks like we got a spammer. Block that dude. Bye, Felicia. Okay, so our buffer size of 10, so I guess the biggest datagram we can send is 10 bytes. Listing 59.3 shows a server program. The server uses the N2P function to convert the host address of the client obtained via receive from call to printable form, so that we can log it probably. The client program is shown in listing 50. I'm kind of curious because like IPv4, there's like a one-to-one between the binary and the printable formats. But with IPv6, there's multiple ways that you can represent an IPv6 address, like especially if it has multiple runs of zeros. And so like IPv6 has this concept of like a canonical representation. So I'm wondering if it uses that or if it like has some other representation that it uses. All right, let's continue reading. Oops, sorry, I'm on the wrong page here. Let's continue reading from here. The client program shown in listing 59.4 contains two notable modifications from the earlier Unix domain version. The first difference is that the client interprets its initial command line argument as the IPv6 address of the server. The remaining command line arguments are passed as separate datagrams to the server. The client connects the server address to binary form using INET Python. The other difference is that client doesn't bind its socket to an address, as noted in section 58.6.1. If an internet domain socket is not bound to an address, the kernel binds the socket to an ephemeral port on the host system. We can observe this in the following shell session log, where we run the server and the client in the same host. So we got the server running here in the background, and then we use a client. We connect to localhost. That's what this is. And we have the string ciao sent to the server, and the response that comes back is all capital. Server received 4 bytes. So this is coming from the server. It says I received 4 bytes from localhost on port 32770. So that's probably the client port there. From the above output, we see that the server's received from call was able to obtain an address of the client socket, including the ephemeral port number, despite the fact that the client did not use bind. Yeah, clients don't need to do a bind. Sushi was chatting earlier about some Go stuff. Not sure if he's stuck around or not. Okay, so we got our main program here for the server and the client. So let's go over the server. So we create our socket. Our socket is an INET6 datagram socket, so it's going to be unreliable. And then this is just going to initialize our server adder that we're going to bind to. We then bind to it here. Once we've bound to it, then we basically call receive from to get a message written into buffer. Buffer was allocated up at the top here to be buffer sized. And then we convert the network representation to a printable representation. And you can see here we also have this client adder, which is allocated up here, where this guy here. And we say, hey, grab the IPv6 address, and we're going to write that into this client adder string. And then if we get that out, then we can print out the client adder string here. If not, then we just print out, couldn't convert the client address. We also print out the client adder port, but we use %u. I'm not familiar. Is that unsigned integer? What is %u format string in C? Yeah, unsigned integer. Okay. We then go through each byte and we update the buffer by converting the byte to an uppercase byte. And then we send to the same buffer to the client address. And then the client just calls socket again with the v6 datagram. The client needs to know where the server was listening on. So if you go back to this bind here, that came from SV adder. So the port number basically that was defined up here is going to be the known location for the server. So the client's going to connect to that, or not connect to it because it's a datagram, but it's going to receive from that and send to that specific port. So it sets up its server adder structure here, and then it tries printing out, or at least converting the server adder's address from argv1. How is it invoked here? Yeah, so it gets the IP address from the argument. So it doesn't necessarily have to be localhost. It can send it anywhere. It then goes over every other argument, sending it to the server, and then receiving the response back and printing it out. Pretty straightforward. All right, DNS. Domain name system. This is going to be a huge review because I think most people are familiar with DNS already. But yeah, let's get through it. Section 5910, we describe get adder info, which obtains IP address corresponding to a host name, and get name info, which performs the converse task. Which would be the RDNS task, I guess. However, before looking up these functions, we explain how DNS is used to maintain the mapping between host names and IP addresses. Before the advent of DNS, mappings between host names and IP addresses were defined in a mutually maintained local file etc hosts containing records of the following form. The get host by name function, the predecessor to get adder info, obtained an IP address by searching this file, looking for a match on either the canonical host name, i.e. the official or primary name of the host, or one of the optionally space delimited aliases. So etc host is similar to etc services. Services in that it's mapping names to, in this case, port numbers, but host is similar. It maps IP addresses to names. However, the etc host scheme scales poorly and then becomes impossible as the number of hosts on the network increases, e.g. the internet with millions of hosts. DNS was devised to address this problem. The key ideas of DNS are as following. Host names are organized into a hierarchical namespace. Each node in the DNS hierarchy has a label, which may be up to 63 characters. At the root of the hierarchy is the unnamed node, the anonymous node, or the root node. A node's domain name consists of all the names from that node up to the root concatenated together, with each name separated by a period. For example, google.com is the domain name for the node Google. technically it's google.com dot. There's a dot for the root at the end. A fully qualified domain name. That's a fully qualified domain name, such as kernel.org dot. Identifies a host within the hierarchy. A fully qualified domain name is distinguished by being terminated by a period, although in many contexts the period may be omitted. No single organization or system manages the entire hierarchy. Instead, there's a hierarchy of DNS servers, each of which maintains a branch, a zone of the tree. Normally, each zone has a primary master name server and one or more slave name servers. It's not very politically correct terminology anymore. Sometimes also known as secondary master name servers, which provide backup in the event that the primary master name server crashes. Zones may themselves be divided into separately managed smaller zones when a host is added within a zone or the mapping of a host name to an IP address is changed. The administrator responsible for the corresponding local name server updates the name database on that server. No manual changes are required on any other name server database in the hierarchy. Zoom into the terminal. Yeah, I think what I'll do is I'm gonna edit. Was it config hyperland, or is it monitors maybe? Yeah, this GDK scale, I'm gonna do 1.8. So let me know does that feel big enough for streaming? A 1.8. Instead of zooming in constantly, I'm just gonna like change it. Maybe a 1.9 would be better for streaming. 1.875. 875. Can I do one? I can't do 1.9. What? Monitor. Okay. We'll keep this at 1.8 then. Can I do 2 on GD keys? No. What if I do 2 here? Yeah, it's the monitor setting that actually changes the scale. Okay, this is just an environment variable here. Maybe 2, was it 2.2? No, it doesn't like that. 2.25? 2.24. $2.1. Okay, it doesn't like that. We'll stick with 2. Yeah, that feels good. Okay, where did we leave off here? We're talking about fully qualified domain names, master slave stuff. I think we're here. Yeah, 2 is great. Okay, cool. Thank you. All right, so the DNS server implementation employed by Linux is widely used Berkeley Internet Domain Bind implementation, named maintained by the ISC. The operation of this daemon is controlled by the file etcnamed.conf. The key reference on DNS and bind is so-and-so. Information about DNS can be found so-and-so. Cool. When a program calls getAddressInfo to resolve, I obtain the IP address for domain name. getAddressInfo employs a suite of library functions. Resolver library that communicate with the local DNS server. If the server can't supply the required information, then it communicates with other DNS servers within the hierarchy in order to obtain the information and do like a recursive resolution. Occasionally, this resolution process may take a noticeable amount of time. The DNS servers employ caching techniques to employ unnecessary communication or frequently required domain names. Using the above approach allows DNS to cope with large namespaces and does not require centrally managed names. I guess it's acceptable that he put all this stuff in here, but it feels like this is just a bunch of like networking review. Like we're not actually talking about like the it seems like we're just learning about DNS. It's like I don't need to learn about DNS. I want to learn about how Linux resolves names, not how DNS works. But it is what it is. Okay, so yeah, this is how DNS works. Great. Recursive and iterative resolution requests. DNS resolution requests fall into two categories, recursive and iterative. In a recursive request, the requester asks the server to handle the entire task of resolution, including the task of communicating with any other DNS servers. If necessary, when an application on the localhost calls get_info, the function makes a recursive request to the local DNS server, and then that DNS server is referred to as a recursive server. If the local DNS server does not have the information to perform the resolution, it resolves the domain name iteratively. Yeah. We explain iterative resolution via an example. Suppose that the local DNS server is asked to resolve the name so-and-so. To do this, it first communicates with one small set of the root name servers that every DNS server is required to know about. We can obtain a list of these servers using dig, blah, blah, blah. Given the name so-and-so, the root name server refers to local DNS server to one of the NZ DNS servers. So Michael Karisk is from New Zealand, so that's probably why he has this as an example. The local DNS server then queries the NZ server with the name so-and-so and receives a response referring to it, the ac.nz server. The local DNS server then queries ac.nz server with the name so-and-so and is referred to ontego.ac.nz server. Finally, the local DNS server queries that server with the name www and obtains the required IP address. Yep. If we supply an incomplete domain name to get host by name, the resolver will attempt to complete it before resolving. This is where it uses the search prefixes or postfixes, suffix, prefix. It'd be suffix, I think. The rules on how a domain name is completed are defined in Etsy Resolve. By default, the resolver will try at least try completion using the domain name of the local host. For example, if we're logged into a machine, and we type the command ssh octavo, the resulting DNS query would be octavo.tago.ac.nz. Okay. Top level, he didn't mention search. That's interesting. Top level domains. The nodes immediately below the anonymous root form a so-called top level domain. Below these are secondary level domains, so on. TLDs fall into two categories, generic and country. Historically, there were 7 generic TLDs. Most of these considered international. We've shown 4 of the original generic TLDs, and blah, blah, blah. Each nation has corresponding country TLD, which is 2-character name. This is all generic stuff we already know. Okay. Etsy services file, as noted in section 58.6.1. So he is talking too much generally when he is going to get into Linux core, what really Linux is doing behind doors. I don't know, like it seems like he's just like touching on all this generic stuff. We'll see. As noted in section 58.6.1, well-known port numbers are centrally registered by IANA. Each of these ports has a corresponding service name. Because service numbers are centrally managed and are less volatile than IP addresses, an equivalent of the DNS server is usually not necessary. Instead, port numbers and service names are recorded in the Etsy services file. The getAddrInfo and getNameInfo functions use the information in this file to convert service names to port numbers and vice versa. The Etsy services file consists of lines containing 3 columns as shown in the following examples. The protocol is typically either TCP or UDP. The optional space-delimited aliases specify alternative names for the service. In addition to the above, I've never used aliases like in the Etsy hosts. Maybe I have. What I normally do is I just copy the line and just have like multiple canonical names for the same IP address. I might have used aliases at some point, but yeah, I don't really remember doing that. As noted previously, a given port number refers to distinct entities for UDP or TCP, but IANET policy assigns both port numbers to a service, even if the service uses only one protocol. For example, Telnet, SSH, HTTP, and SMTP all use TCP, but the corresponding UDP port is also assigned to these services. Conversely, NTP uses only UDP, but the TCP port 123 is also assigned to the service. In some cases, a service uses both UDP and TCP. DNS and Echo are examples of such services. What? Echo? What is Echo? I know DNS does TCP and UDP. Cat Etsy services, grep out, Echo. What the hell is this Echo server? How have I never used this? What is the Echo port 7 service? Like, I've written Echo servers before. Security. Yeah, amplification and reflection attacks, especially for UDP. Many DOS techniques. DDoS techniques. Historically used Echo style services. Yeah. I mean, having an Echo server on UDP would be basically a reflection or amplification attack. So when we usually get connected via the labs during CTFS, there's need to do so via the VPN. Okay. Where are we at here? We're talking about Echo. Where's Echo at? Echo, DNS, and Echo are examples of such services. Finally, there are very few cases where the UDP and TCP ports are within the same number are assigned to different services. For example, RSH uses TCP port 514, while a syslog daemon uses UDP port 514. This is because these port numbers were assigned before the adoption of the present IANA policy. The Etsy services file is merely a record of name-to-number mappings. It is not a reservation mechanism. Could you imagine someone editing this file and be like, I reserved it? That's so silly. The appearance of a port number in Etsy service does not guarantee that it would actually be available for binding by a particular service. That's funny. Protocol independent host and service conversion. The getAddrInfo function converts host and service names to IP addresses and port numbers. It was defined in POSIX1G as a reentrant successor to the obsolete getHostByName and getServiceByName functions. Replacing the use of getHostByName and getAddrInfo allows us to eliminate IPv4 versus IPv6 dependencies from a program. The getNameInfo function is the converse of getAddrInfo. It translates a socket address structure to the corresponding to strings containing the corresponding host and service name. This function is the reentrant equivalent to the obsolete getHostByAddr and getServByPort functions. Okay. The getAddrInfo function. Given a host and a service name, getAddrInfo returns a list of socket addresses. We already read the man page for this. I'm just going to skip over that. He might get into some more detail here. Oh, he has a little diagram here. That's nice. Hints argument. So this is all that function. Freeing, diagnosing errors. Get name info function. Okay, and then we do the client server examples. An internet domain sockets library. Obsolete APIs, and then we get into a summary. Unix versus internet domains. Okay. This is like a lot of stuff. Okay. In capture the flags, we often add loopback IP or hostname address aliases to localhost to simulate multiple services or hosts. That's cool. Yeah, I haven't done any capture the flags before. But yeah, obviously, like editing Etsy host is like a good way of intercepting traffic to services, getting in between the application and the service. All right. As input, get adder info takes the arguments host, service, and hints. The host argument contains either a host name or a numeric address string expressed in IPv4 dotted decimal notation or IPv6 hex string notation. To be precise, get adder info accepts IPv4 numeric strings in the more general numbers and dots notation described in section so-and-so. The service argument contains either a service name or decimal port number. The hints argument points to an adder info structure that specifies further criteria for selecting the socket address structures returned via result. We describe the hints argument in more detail below. As output, get adder info dynamically allocates a linked list of adder info structures and sets result pointing to the beginning of this list. Each of these adder info structures includes a pointer to a socket address structure corresponding to host and service. The adder info structure has a following form. So we got our flags, family, socket type, protocol, adder length, and canonical name. That was not in that structure when I read the man page. Let's go back to the man page. Yeah, they did not have that documented here. So they got flags, family, sock type, protocol, adder length, adder. Okay, so the adder was replaced. So this canonical name was replaced with this adder structure here. Sock adder. And then we got next and okay, so canonical name's just missing because that adder structure's here. So canonical name is missing in this thing. Yeah. Wonder why it's missing. Seems important. A char star. All right, the result argument returns a list of structures rather than a single structure because there may be multiple combinations of host and service corresponding to the criteria specified by host, service, and hints. For example, multiple address structures could be returned for a host with more than one network interface. Furthermore, if hints AI sock type was specified as 0, then two structures could be returned, one for datagram and the other for stream socket, if the given service was available for both UDP and TCP. The fields of each adder info structure returned via result describe properties of the associated socket address structure. The family field is set to either INET or INET6, informing us of the type of the socket address structure. The socket type field is set to either sock stream or sock dgram, indicating whether the socket structure is for a TCP or UDP service. The protocol field returns a protocol value appropriate for the address family and socket type. The three fields, family, socket type, and protocol, supply the values required for the arguments used when calling socket to create a socket for this address. The adder length field gives the size and bytes of the socket address structure pointed to by adder, and the adder field points to the socket structure, either sock adder in for v4 or sock adder in 6 for v6. The flags field is unused. It is used for the hints argument. canonical name field is used only in the first adder infrastructure and only if canonical name is employed in the hints flags as described below. As with get host by name, get adder info may need to send a request to a DNS server, and this request may take some time to complete. The same applies for get name info, which we described in section 59.10.4. We demonstrate the use of get adder info in section 59.11. So here we go. We got a result pointer. So if you go back to the prototype, result is a pointer to a pointer. So we get back the pointer, or the pointer to the pointer is where we write where the function writes the pointer for the result, and then it points to the first adder info structure, which I guess could have this canonical name thing, but I didn't see it in the man page. And then this is a linked list that then has n number of things that it points to. Each one of them has an adder, which could be IPv4 or IPv6 adder structure. The hints argument. The hints argument specifies whether further criteria for selecting the socket address structure returned by get adder info. When used as the hints argument, only the flags, family, socket type, and protocol fields of the adder infrastructure can be set. The other fields are unused and should be initialized to 0 or null as appropriate. We got another spammer. We got plenty of spammers this morning. All right. The hints AI family field selects a domain for the return socket address structures. If it may be specified as inet or inet6 or some other constant if the implementation supports it. If we're interested in getting back all types of socket address structures, we can specify the value unspecified for this field. Socket type specifies the type of socket for which the return address structure should be used. If we specify this field to be dgram, then a lookup is performed for the UDP service, and a corresponding socket address structure is returned via result. If we specify stream, a lookup for the TCP service is performed. Sock type, if socket type is specified as 0, any socket type is acceptable. Protocol field specifies socket protocol for the return address structure. For our purposes, the field is always 0, meaning that caller will accept any protocol. Flags. The flags field is a bit mask that modifies the behavior get adder info. This field is formed by ORing together 0 or more of the following values. So we got adder config, all, canonical name, numeric host, numeric service, passive, and v4 mapped. So adder config, return the v4 address only if there is at least one v4 address configured for the local system other than the v4 loopback address, and return v6 addresses only if there is at least one v6 address configured for the local system. So that's to prevent you trying to speak IPv6 or IPv4 if it's not supported on your local system. So then Twitch algo is working the recommendation. Yeah. I don't know how any of this stuff works, to be honest. I'm streaming to Twitch and YouTube now. I'm thinking about streaming to some other platforms. But for now, I figured it's YouTube and Twitch. And it seems like I get more viewers on Twitch. I mean, not a lot. But yeah, I'm just getting started here. So, but it seems like Twitch is a little bit more active in people joining and chatting, whereas YouTube, sometimes people will pop in, but for the most part, like I've only had a few people chat on YouTube. AI all, which is something related to the v4 mapped. Canonical name, if host is not null, return a pointer to null terminated string containing the canonical name of the host. This pointer is returned in a buffer pointed to by canonical name field of the first of the adder info structures returned via result. Numeric host, forced interpretation of host as a numeric address string. This is used to prevent name resolutions in cases where it is unnecessary, since name resolution can be time consuming. Numeric serve service as a numeric port number. This flag prevents the invocation of any name resolution service, which is not required if service is a numeric string. If you already have the numeric host and numeric service, you can just connect to it. You don't need to. You can just create the socket. And I don't know why you would even call into this function if that was the case. Maybe you have a numeric host, but you want to resolve the service and vice versa. But if you're not doing any resolution, it doesn't make sense. Passive returns socket address structures suitable for a passive open, a listening socket. In this case, host should be null, and the IP address component of the socket address structure returned by result will contain a wildcard IP address. If this flag is not set, then the address structure returned via result will be suitable for the use of connect and send to. If host is null, then the IP address in the returned socket address structure will be set to the loopback IP address. V4 mapped. If inet6 was specified in the family field of hints, then IPv4 mapped IPv6 address structures should be returned in result if no matching IPv6 address could be found. If all is specified in conjunction with v4 mapped, then both v6 and v4 address structures are returned in result, with IPv4 addresses being returned as v4 mapped v6 address structures. As noted above for AI passive, host can be specified as null. Let's see here. So host can be specified as null. It is also possible to specify service as null, in which case the port number in the returned address structure is set to 0. I.e., we are just interested in resolving host names and addresses. It is not permitted, however, to specify both as null. If we don't specify any of the above selection criteria in hints, then hints may be specified as null, in which case socket type and protocol are assumed as 0. Flags is assumed as v4 mapped and or in combination with adder config. Family is assumed to be unspecified. The glibc implementation deliberately deviates from susv3, which states that if hints is null, flags is assumed to be 0. Freeing adder info lists. Let's see. So I have a suggestion in OBS. You can add browser overlay. Let's see. If we can add some custom widget there, we can add the time, number of pages, goals, host that code locally, and then import that so that OBS browser overlay. I don't know. To be honest, I do not know. I've done a little bit of that, not with the browser overlay. I've used the OBS built-in overlays. Yeah, I mean, if you want to send me something, I'll look at it. I guess, you know, I feel like, I mean, I'm just getting started here, but I feel like one of the things I want to continue doing is having a minimal overlay on the stream, because I see a lot of Twitch streamers, or a lot of streamers in general, that have like all these like notifications and like all this like garbage on the screen. And I was actually questioning whether I should even have my webcam. Like, I mean, I think having a webcam is nice in that it's like proof that I'm an actual human being. Whereas if I was just like talking into a mic with the screen, like people would be like, well, it could be AI generated, you know. So it's like proof that I'm human. But even now with AI, like you can fake video, but I don't know. I feel like it sends a signal that there's someone at the other end here, an actual human being. Yeah, it does prove that it's live. I was thinking about doing the actual chat as an overlay. Like there's a Zig project. Let me pull it up on screen here. There is this thing. Oh, sorry, wrong one. Zig Twitch chat. Is this a Bork? Is this the one? Yeah. So I saw Andrew, the guy who created Zig, was using this for some of his streams. And it actually uses, like, you have to have a terminal that supports the, like, drawing images. The Kitty protocol or whatever it's called. And I don't think Alacrity supports that, but I don't really care. The point being that this seems like a really nice UI for doing Twitch chat, and having that even just loaded up on the streaming machine that I have might be interesting. Yeah. The problem is I think it's Twitch only right now. Yeah, it's currently in alpha stage, and it's meant for Twitch. And on the side of my screen, I have Twitch chat and the YouTube chat loaded up. So like it would be cool if they like extend this for multi-streaming, so you just have like one chat for all of your different streaming platforms or whatever. But yeah, I don't know, that if you want to send me something in Discord, I'll definitely take a look at it. But yeah, I'm not really like eager to add overlays and stuff quite yet. All right, so where do we leave off here? Oh, okay. So one of the things that was obvious to me in looking at this prototype is that because we're passing a pointer to result, like we're not giving it memory to allocate or to utilize for writing the results. We're saying when you go ahead and create the result, and then when you're done, here's the place where I want you to store the pointer to that result. And because of that, that means that the getAtterInfo function does its own heap allocation. In addition to that, because it's a linked list, it's definitely doing heap allocation because it has pointers to arbitrary parts of memory here. It's not like an array structure. So because of those two things, basically like there's heap allocated memory, which means that when you call the function, you are responsible for actually freeing that memory. So they have a section here on that. The getAtterInfo function dynamically allocates memory for all of these structures referred to by result. Consequently, the caller must deallocate these structures when they're no longer needed. The free AtterInfo function is provided to conveniently perform this deallocation in a single step. So you just give it the pointer to the result, and it goes through and it frees everything for you. If you want to preserve a copy of the AtterInfo structures or its associated socket address structure, then we must duplicate the structure before calling the free AtterInfo. Pretty straightforward. Yeah, I was actually thinking about possibly doing that at some point, like customizing that project for like adding YouTube chat support. I've done a little bit of like chat programming on Twitch ages ago. Via IRC, because Twitch chat at the time at least was like IRC driven. So wiring it up to YouTube, I think it would be pretty straightforward, but yeah, not super familiar with Zig, but it seems like it'd be easy. Okay, so let's see. We got about 2 pages left before we get into the client server example that they have in the book here. So I think I might break there for lunch. So let's go ahead and get through this. So diagnosing errors with GAI stir error. Basically, there's all these errors that come back from the function. Given one of the error codes, GAI stir error function returns a string describing the error. The string typically briefer than the description shown in table 59.1. So if you go here, that's just a little helper for getting the error string. We can use a string returned by that as part of an error message displayed by an application. The getNameInfo function is the converse of getAddrInfo. Given a socket address structure, either IPv4 or IPv6, it returns strings corresponding to containing the corresponding host and service name, or numeric equivalents if the names can't be resolved. I don't think there's anything interested in reading here on that. It's just the inverse, which is very rare that you'd actually need to use this. So I'm going to say let's go ahead and wrap the stream here. I've been going for a little over 2 hours. And I'm going to grab some lunch because I'm starving. And when I get back, I will resume on client server example, which is just a bunch of code and running the client and server. I wonder if they use threads on this server. I'm kind of curious. I'm going to cheat here and look ahead a little bit. No, they don't use threads. So it's not really a great server. It's a single threaded iterative server. So yeah, they do like a basic client server example with streaming sockets, and then they have a section on this library that they wrote, that Keras wrote, which is probably not something I'm going to ever use, but we'll review it. And then he talks about some obsolete APIs, which I might even just skip over because I don't care about obsolete APIs. And then a discussion on Unix versus Internet Domain Sockets and a summary. So I think the game plan for the start of next stream is to get through this client server example really quickly because it's not a great server. It's like an iterative single-threaded server. And then maybe do a brief overview of the library that he presents. And then just skip over the obsolete APIs, and then we'll wrap up the chapter sections for Unix versus Internet Domain Sockets. So I think that'll get us through this chapter probably within an hour, I would say, if not less. And then we'll be on chapter 60, which is server design, which is more interesting to me than the server that they present here. Let's see. Okay, I'm gonna go ahead and end the stream there then and grab some lunch, and I will be back probably around 1:45 my time. So about we'll just say 2 hours, because I got some stuff to do. So cool. If you hop on then I'll see you then. Later. Bye.